12. Shall we start?
Yes.
Right. Okay. So welcome to the ICC internal seminar this week. We have Tristan Cantat. He's telling us about galaxy structure using, I suppose it's using a Gaia data.
Yes, there will be a lot of Gaia data.
Excellent. Okay, please go ahead. We have some break in the midpoint of your talk. Is that okay?
Yeah, sure. And I mean,
Okay.
you can ask questions whenever you want.
Right.
So I'll be presenting the work I've been doing on the Milky Way and using Gaia to estimate the structure of our host galaxy. And just to start, these are the credits. My main collaborators in this work are from Barcelona, from Bordeaux, from the University of Lisbon, and collaborators in Italy and even in California now. And so this has been a group effort. And the object of my research is the Milky Way. And we know that the Milky Way is a spiral galaxy, but something that's always been a paradox to me is that we know other spiral galaxies much better than we understand our own, because we can see them in their entirety. We can see them from outside, and so we can understand their structure, their dimensions. And there's a broad variety of types of spiral galaxies. Some have very tightly wound arms that actually look like they melt into each other. Some have much more separated arms. Some have two arms, some have more. And some have a very prominent central bulge, and some do not have that. And we cannot really tell exactly where our galaxy stands in that variety of types of galaxies. Because we're inside. So whenever you see something like that on TV, in a movie, in a magazine, it's not literally an observation. It's always a reconstruction, and it's actually most of the time an artistic view. If you type Milky Way structure from outside something in Google, you see very, very different kinds of galaxies because we don't really know what our own looks like. So sometimes they're models, sometimes they're pure artistic inventions. Because what we see from our point of view is something like that. We can tell we're more or less inside a flat structure because it looks like a stripe in the sky, but we cannot tell much more because we lack the depth and the distance to all these different blocks of the Milky Way. The oldest attempt that I know of at understanding the overall structure of the Milky Way was what William Herschel did in the late 19th century. So he found a way to estimate the mean distance in different lines of sight. And so he came up with that sort of elongated thing. I think on the left of the picture, that would be what we know now to be the inner Milky Way, and on the right, the outer Milky Way. He thought we were more or less at the center because everything seems to be more or less equidistant from us, all around us. And well, obviously there's a lot he couldn't know about the physics of the stars and everything, but conceptually that was a very interesting idea. And what we see now with the most exquisite map of the Milky Way we can build, this is from the Gaia data. This is the Gaia DR2, so the second Gaia data release. And it's very precise. We can see a lot of features and extinction. So this is due to dust, and there are more stars in the center. But this is still flat. It looks really nice, but basically it's the same as this, but just all sky and more precise. And if you look at the Milky Way in different wavelengths, TUMAS is a survey that does near-infrared photometry, so it can see through the dust a lot better than Gaia. So the galaxy looks flatter and less irregular, but you still don't have the distance, you don't have the depth, and you absolutely do not see any kind of spiral structure with this. And you can combine all of these with like infrared observations or ultraviolets, but what you need to find the structure is still the distance. A common kind of object that people have been using to disentangle the depth and the 3D structure of the Milky Way are star clusters. Stars that are in a cluster, they are the same age and they have the same chemical composition because they come from the same cloud of gas. And all of these stars in a cluster, within a cluster, they're still bound by gravity. And they can be found pretty much everywhere in the galaxy and at many different ages. And that's something I find really interesting with star clusters is some of them are very young, a few million years old. Some of them can be as old as several billions of years. So they span a wide range of ages, and we can estimate that age. There are other tracers that people use. For instance, there are kinds of variable stars that called Cepheids, and you can find their distances, but all the Cepheids are very young objects, or stars called RR Lyras that also have precise distance estimates, but they're all very old. And something I like with clusters is with the same method, you can find very young or intermediate or old clusters. So not only they can give you the 3D structure of the Milky Way, but you can also study how it evolves through time, because old clusters might be distributed differently from young clusters. The oldest example I know of, and I really think that's the oldest example, of someone using star clusters to find the 3D structure of the Milky Way was this paper by Trumper in 1930, so that's almost 100 years ago. And he thought again that we were at the center of the Milky Way. And he found the distance to many different, about 200 clusters maybe. And with the data he had back in the day, that was really good. And I think he overinterpreted his data because he tried to draw spiral arms on top of this. So even back then, people already knew we were in a spiral galaxy, but he thought it was a small galaxy. We know now that actually the entire Milky Way would be larger than the screen on this slide. But still, he was looking for a spiral pattern because that's the hint. You cannot see the spiral pattern from the images, but people knew somehow there had to be a spiral inside the Milky Way. He didn't estimate ages because we didn't know enough about stellar evolution back then to be able to actually estimate ages. So in a way, we will be using some of these concepts, but with Gaia data. So it will be a lot more precise and the stellar evolution models are better. But the idea to use clusters as individual points to trade the structure is still something we're doing now, and we'll be doing this for a while, I think. I'm not going to be talking about Gaia specifically because everyone here probably has heard too much about Gaia, but I will be saying what Gaia does for me, for my work. And so I'm going to show what a cluster looks like in the Gaia data. First, on the left, this DSS image. So DSS is the Digitalized Sky Survey. So they're basically photographs of the sky in optical. And you can see this example cluster, NGC 2509. You can spot that it's a cluster because, well, there's a concentration of stars in the center. But where does it end? Where exactly are its limits? That's not clear. If you look at the same cluster in the pan-stars, which is mid-infrared, infrared observations, you can see an overdensity, but again, there's a lot of background contamination. And here in a circular field of view in the Gaia data, I think we can see more clearly a concentration, and then the outskirts are less dense. And that's because Gaia doesn't just measure the positions of the stars in luminosity, but also their what we call proper motions, so how they move across the sky, and their parallaxes, which are swords-like having distances. So you can really select the stars that are the most likely to belong to the cluster. And you don't have this background or foreground contamination. Actually, if you look at this cluster in the Gaia data on the sky, you don't see a very clear concentration. I mean, maybe you see it because I tell you it's there, but you wouldn't be able to spot it. But if you look at those exact same stars in proper motion space, we can see some stars are moving to the left, some to the right, to the top, to the bottom, north, south. But there is this very clear concentration here. These are about 1,000 stars moving all together. And if you select those and you plot their distribution on the sky, here you can see a clear central concentration, and you can see the trace in photometric space, which means if you plot the luminosity of stars against their color, you can see how neatly there is this very, very clear alignment and clear presence of red giant stars. So if I look at this, I can say directly, just by selecting by hand, I say, okay, this is a very old cluster, it's maybe 1 billion years old, because I'm used to seeing images like that. But this cluster that's very, very clear, actually until a few years ago, it was a borderline case that different studies would disagree on the distance and the age. So it was a difficult cluster. Now it's not a difficult cluster, it's a very obvious one. So everything that was borderline before Gaia is now very easy, and things that were impossible became feasible. You don't need to read this because it's boring, it's a lot of text, but basically I'm listing what I think were the most relevant and useful all-sky searches for clusters in the Gaia data, and people finding hundreds, thousands of clusters in Gaia. And now we have about 2,000, maybe more, confirmed clusters that were found, that were confirmed to exist in the Gaia data. Interestingly, there are hundreds, even about 1,000 objects that were known before Gaia, and we couldn't find it with Gaia. We can't find these objects, and they should be easy. I mean, if they were discovered in the 19th century by people looking at the sky without even taking photographs, well, Gaia should find them. So this was an interesting issue, and our conclusion for many of them is that they don't exist. It was an idea that was hard to push, so we dedicated with Friedrich Anders from Barcelona an entire paper to this. Here that would be a side view of the Milky Way. So on the left, the inner Milky Way, and on the right, the outer Milky Way. And every white dot is a cluster that was confirmed to exist, and the empty symbols are those for which we have, with a high degree of confidence, we think that they are not real clusters. And it's interesting because it shows that the inner Milky Way, at least traced by clusters, is not very fluffy at all, but the outer Milky Way is. If you add the empty circles, it's telling you a complete different story. So cleaning the lists, cleaning the catalogs was actually, I think, the most immediate achievement of Gaia for the cluster studies. But you can easily see how before having Gaia, people would think, well, these are 4 bright stars together. Maybe that's a cluster. Maybe this is a cluster. Maybe this could be a cluster. But now with Gaia, we can see these stars are flying in completely different directions. They're not even at the same distance. So I think it was quite interesting to be able to say that people 150 years ago made mistakes in their classification. Many NGC clusters, so NGC is a catalog that was built at the end of the 19th century. Many of them are real and they're very interesting objects, but still a significant fraction was not true clusters. And well, so after cleaning the lists, we focused on every cluster that is real, and we found a way to estimate the main parameters. So for me, the main parameters to clusters are their distance and their age. And what we needed was a method that was able to deal with all of these clusters at once. Some are very nearby and have many stars. Some are very distant or very sparse. Some have a very clear color magnitude diagram, some have more blurred photometry. But what I wanted is a method that is not necessarily the most precise, but a method that would work for every object, a reasonable estimate for all of them. Very nearby, very massive, or very distant, very sparse clusters. And the method I used was based on machine learning. Again, there's a lot of text. You don't need to read all of that. You can just look at the pictures if you want. I'm looking at 2 different color magnitude diagrams here, one for a young cluster on the left and an old cluster on the right. If you're used to working with this kind of data, it's obvious here that the one on the right is old because it has red giant stars, and in the other one, the brightest stars are very blue. But I wanted something that was more quantitative than that. And I thought, if I can teach a computer what an old cluster looks like, what a young cluster looks like, and some are old and nearby, some are old or distant. So there's all the different combinations of parameters. But if I could teach a reasonable, from a reasonable training set, tell the computer, okay, this cluster is 1 billion years old, this one is 10 million years old, maybe it could extrapolate this knowledge from a few hundred clusters with well-determined parameters to the entire set of 2,000 known clusters. And that would be able to refine the ages of the clusters that are already known, and for the first time give an age estimate for everything that has just been discovered recently in the past few months. So I taught this neural network how to estimate the age, the distance of a cluster with a combination of photometry and Gaia observation, and the reddening, because if you have dust or gas in front of a star, it makes it redder. So you cannot directly say that red stars are old, because maybe there are young stars that are being reddened by a cloud of gas. So you have to disentangle all these effects. I'm showing this complicated figure. It's actually the typical architecture of a neural network. The only interesting things that you need to remember here are the input and the output. The input in that case is the Gaia photometry. So I'm showing a histogram to the neural network, a histogram of the color magnitude diagram, plus a few other measurements like the mean color of the faint stars and the Gaia parallax. And from this, I get an estimate of the age, an estimate of the reddening, and an estimate of the distance. I think one of the flaws in it, not a flaw, but something that we could do if we want to go beyond, is that I require every star in this work to have a measurement of its luminosity, its color, its parallax, etc. I would like to be able to combine this. Maybe one of these stars also has spectroscopic measurements, or one of these stars has been observed by a different instrument. So if we could add all of this, we could maybe have more constraints on the parameter of the cluster. But so far, I think that's really reasonable kind of output. Another thing I would like to be able to do next is estimate the metallicity, so maybe the chemical composition of the cluster. It's a slight change in the color magnitude diagram, so it's a second order effect. But I think it's also something technically we could be doing with the Gaia data and machine learning. But we didn't do that. So far we only have those three outputs. We refined for some objects that were thought to be very young. Actually, now with Gaia, you can show that they're very old, and vice versa. Some clusters, they were believed to be old, and actually they're very young reddened clusters. Most of the time, you can see this correlation that, okay, stuff that was thought to be old is actually old. Young clusters, well, there's maybe a 50% chance, 50% chance that it's actually not a young cluster, and Gaia shows it's old. This is not, I'm not claiming that my method is better than anything that was done before, but it's efficient, and this is mostly by virtue of having the Gaia data to have precise membership probabilities. You can know which stars are members of the cluster, so you can really clean your procedures. And once you have all of this, what I'm mostly interested in is the distance and the age. Well, we can go back to doing this kind of maps, but with the Gaia data. So what we see now, this is the map we got. Again, the sun will be at the center, because most of the things we can see are surrounding us. Things that are too far, we cannot see them. So I'm sorry if you're disappointed and you saw the first images of spiral galaxies and you thought, okay, we can see our galaxy like that now. So no, at the moment we cannot, but we're starting to see some correlations, some patterns, like this is associated with a spiral arm. And in a way, this starts correlating with the known pattern that was estimated from other methods in the disk. This is better than we had before. This would be what you would be looking at if you used things that were measured before Gaia. So the distances are not that good. The age estimates are not that good. A lot of these points are clusters that don't actually exist. So this would be the improvement we've had with the second Gaia data release. And so this is better because we have only clusters that are real. We have more points because we have more clusters, better distances and better ages. Still, the structure seems interrupted. For instance, the outer arm that some people see in the literature, we don't seem to see it at all in the cluster distribution. So maybe these are just too far away and we need to look at more clusters in that direction. And one of the things that I found most interesting, and we focused on that later, is this apparent gap here. This would be what is called a Perseus Arm, and there are no clusters here. And it was noticed actually before Gaia, but people thought maybe our view is blocked. Now with Gaia, we can tell our view is not blocked because there are objects behind the gap and we see them. We just don't see what's inside. And several papers have focused on trying to find the objects in here, and we never found anything, but we find things that's behind or on the side. So by contrast, actually the gap is even clearer now. Here I'm focusing specifically on this region. So this square box here would correspond to this region here. The sun is here, and on the line of sight, we can see on our right clear overdensity of clusters, and on the left, we also see a slight overdensity. And in the middle of the gap, there's an overdensity of things that are behind. One of the explanations for that would be that this arm is not one single entity, but maybe it would be something that's being torn apart, and it's maybe two different arms that are aligning at the moment, or maybe this plume of stars is something that was part of the gap and is being torn away. And this would mean that, so yeah, to better understand how this is shifting, we would need to look at this in velocity space rather than just in positions. But at least for the moment, I think it's hinting at the fact that the Milky Way might look a bit like this galaxy that people are calling flocculent, where you cannot really trace one single arm all the way from the outskirts to the center. Maybe it's branching out, maybe so. Overall, there seems to be a spiral, an idea of a spiral pattern, but you cannot really follow one arm all the way. And maybe the Milky Way has this kind of pattern in it. That's all I'll be saying about the spiral so far. So if you wanted to take a break or ask questions, maybe we can do that now.
Okay. If anyone has questions, we have a few minutes for that. Are there any questions?
I do have a question.
Yes, please.
Yes, well, two questions. First, why do you need the slopes of the HR diagram if you are using already the whole color magnitude information?
Yeah, that's a good point. So these things, the slope I measure, and even this mean color of the faint stars, it's redundant with the information that's already in the rest. But I found that for the training step, it was making everything a lot faster and less noisy, because sometimes if you provide an input, something that the neural network has never seen, maybe you can get some completely wrong answers. And this was helping a lot mitigate the completely wrong results, something that are unphysical because the neural network doesn't know any physics. So for training, it was a lot faster, and for the quality of the outputs, it was a lot easier. I agree that it's redundant, and in a way, if you provide these three things, maybe you don't even need the others. but having just these three have a lot of weights compared to all the other components in the photometric inputs. So it's redundant, but very useful.
Okay, and well, the other is that about the gap in the Perseus Arm. Have you correlate that with the hydrogen information, not clusters, or?
Yeah, so in other tracers, yeah, there seems to be some discontinuity. So in hydrogen, it seems to be continuous, but also with a kink in velocity, it's hard to trace. And when you want to overlay different kinds of tracers, it's not very easy. But this seems to be overall free of dust, free of gas, free of star formation. And yeah, it correlates with things seen in other wavelengths. But the distance is really the thing that we add here, because we have clusters that have Gaia observations, so we can tell the actual dimensions of the gap.
Okay, Jordi had questions.
Yes, thank you. So, well, thanks. That's really fascinating, Tristan. But so I wanted to ask also, you showed this graph of the new distribution of open clusters, right, in the disk of the Milky Way galaxy, which show the positions, and then you have ages here. So because you have motions, and I assume you also have radial velocities for many of these, then we should expect to find these open clusters in some epicycles that are, populated in a special way because of the spiral arms. So have you tested also the velocities here?
So in the work I'm showing, we haven't looked at velocities, but so it's really hard to use the velocities to identify to separate different spiral arms. But there's a paper, but it's not my work, but Alfred Castro from this institute has looked at the spiral pattern in velocity space. It's not really helpful at the moment to identify the arms themselves, but if you focus on the young clusters, some of them have radial velocities, which means they have the 3D information on their velocity. And we can start seeing the pattern speed of the different arms. And this is work in progress, because at the moment, not all of the clusters have the associated radial velocity. In Gaia DR3, we will have radial velocities for a lot more targets. So this will be investigated, yes.
Thank you.
Okay. Is there any other questions?
So maybe I can move on. I'm more than halfway, so
okay.
The rest. What I think was the most the cleanest results from this analysis that gives us distances and ages. It's not the top-down view of the Milky Way that we looked at, but the one I like the most is actually this side view of the Milky Way, where on the left, so it shows the inner Milky Way, on the right, the outskirts, and the sun will be around 8,000 parsec, so somewhere here. And it really shows that in the inner disk, most of the clusters are youngish, younger than 100 million years. And they are very close to the galactic plane. You don't see any cluster, young or old, away from the disk, so very at high altitude. And in the outer disk is the opposite. Most clusters are old. Still, we have some youngish clusters, but most of them are old, and they can escape out to very high altitudes. And this is the combination of many different mechanisms. I think what we are looking at is that clusters can form, stars form everywhere in the Milky Way, but the stars that remain bound as clusters To remain bound, you need to be born in the outer disk or to move outside, to migrate to the outer disk. If a group of stars is born in the inner disk, it will probably be destroyed very quickly. So these stars are still here, but they're just not clusters anymore. And in the outer disk, out to 14 kiloparsec, we find young clusters. But after that, everything is old, which I think is an indication that there is no star formation happening there. And everything that we find more distant than 14 kiloparsec is something that was born inside and migrated outwards. Or maybe back in the days, back many billions of years ago, it was possible to form stars, but I think it's unlikely. I think it's more the migration scenario. And we can find old clusters over several billion years, very far from the disk. Everything that's far from the disk is old. This is not, the last point is not a very old and not very new and surprising concept. We know that gas is present at high density, very close to the plane, because that's where gravity brings it to the densities that are necessary to form stars. And during their lives, with random encounters with various other objects in the Milky Way, the stars can be kicked out to very high orbits. And the older you are, the more likely you are to be found at a very distant altitude. It's a bit like Brownian motion. We don't know exactly what drives the dispersion yet, but some people think it's a purely diffusive mechanism, exactly like Brownian motion. And what I like is not that this is a brand new revelation, but it's the first time we see it clearly like that, because we have cleaned all the non-clusters. And this part about the cutoff, is there really no more star formation, or is this part empty of clusters in my sample because we have never found them? That's also a question I would like to answer. So we have searches, and now in the new Gaia early DR3 and in the upcoming Gaia data releases, we will be trying to find clusters here. These three, Berkeley 29, Sora 1, Berkeley 20, are they very special objects? Or is there a whole group of objects we could find in this empty region? I think it would be exciting to find the 10, 15, 30 clusters in that region. That would be really cool. To be a bit more quantitative, we tried to fit a model that would explain how the scale height of the clusters depends on their age. Because very clearly, the yellow points, which are the old clusters here, have a larger scale height than the blue points that are the young clusters. And this is actually, so there are strong correlations here, because the high scale heights clusters are also mostly found in the outer disk. And we know that just purely due to the galactic potential, so the fact that most of the mass is in the inner galaxy, we have this triangle shape, and the scale height is naturally larger in the outer disk, even for a given age. If you look at just the blue points, they have this wedge triangle-like shape. So this shape is the combination of two things. The scale height depends on the position in the galaxy, and it depends on the age. And unfortunately, the age also depends on the position in the galaxy, because in the inner disk, things cannot survive. So it's really hard to disentangle this. And again, as Jordi mentioned in his question, we can look at this in velocity space, which is something we have started doing, but I will not be discussing in this talk. And it will help us understand better what are the mechanisms that drive the dispersion of the clusters, and as a consequence, the evolution of the star dispersion in the Milky Way, which means its evolutionary history. What are the main mechanisms that drive the evolution and the shape and the morphology of the Milky Way? Because if we can prove that the mechanisms that disperse the stars are strong enough to destroy the clusters, well, it's interesting, because it means that they are very brutal events. Maybe they are due mainly to satellites interacting with our galaxy, and they throw everything away and then destroy the clusters. Or maybe it's actually something a lot more gentle, like the spiral arms and asymmetries in the galactic potential slowly driving away some clusters. So being able to say, disentangle the combination between the mechanism that destroy clusters and those that just disperse stars, this will be a huge step to understanding the mechanisms that came to give the Milky Way its shape. So soon we will have 3D velocities for a sufficient number of clusters, and that would be really nice. And maybe very quickly, yeah, so a quick thing about the mechanisms that destroy the clusters. Here I focused on a specific region, which is the Vela Puppis region. It's actually several hundreds of parsecs deep and wide, but all of these clusters here are very young. And I'm especially interested in understanding why clusters are dispersed and disrupted, because, so in the previous slide, we see, okay, there are no old clusters in the inner disk. Are they destroyed by some mechanisms, or is it because of the natural process of star formation makes it impossible for clusters to survive? And this is a region where we thought before Gaia that there were 5 or 6 clusters, and they were listed, some of them NGC, blah, blah, blah. They've been known for over 100 years. But if you look at this with Gaia, you don't see 6 clusters. You see a lot of blobs. Some are spherical, some are elongated, some are aligned, and there's a lot of different age groups. And it's not like the top left is one age and the bottom right is a different age. So there's an overlap of different things. And with Gaia, you can look at the velocities of the stars individually within each cluster, and you can tell if they are bound by gravity or not. This one, IC23191, for instance, we can see it's bound by gravity because the stars are rotating around each other. So they feel each other's presence. But maybe if I could do something similar in this Colindo 140 or UBC7, maybe there are too sparse. Maybe they're not massive enough. So maybe these guys are expanding and being completely destroyed. Maybe one of the blobs in this picture is going to survive and become a cluster, or maybe 3 of them. I don't know. And this is something I would like to investigate, because again, that would give us the possibility to understand why the survivability conditions for clusters. Are they naturally disrupted by the fact that star formation is good at forming stars but not good at forming clusters? Or does it mean that if clusters are destroyed, does it mean that a violent event happens? So understanding how this particular region can evolve would help us understand how this picture came to be. And ideally, we cannot do that with Gaia yet, but this Vela region is near the sun. But if we had an equivalent Vela in the outer disk and an equivalent in the inner disk, we could then compare what allows clusters to survive, and does this depend on the position in the Milky Way? So that's the direction I would like to take in the future investigations I will be making, not just clusters tracing the picture of the Milky Way, but also individual motions of stars within clusters. Gaia has made that possible. And this is my last slide. So with Gaia, we have obviously more precise data than before. We have parallaxes. We can clean the color magnitude diagram, and we have the opportunity to have the same perfect data sets across the entire sky, which means every study you make, you can do it for every cluster in the catalog. No more studying 2 clusters, 3 clusters in a paper. No, you can do hundreds in one go. And so far, I think it has shown that in the spiral pattern of the Milky Way is not that obvious. I think if we lived in a very simple galaxy, we would have seen the pattern by now. And the correlation between the age and position in the Milky Way is very clear in that plot, but it's due to many things. The disruption of the clusters, if they die, if they move. So we don't have yet all the elements to tell the evolutionary history of the Milky Way, because we're looking at it in this study in just 3D position. But once we have the velocities, we will be able to tell a lot more. And I think that's a summary of what my research has been about so far. Thank you.
Okay, thank you very much. There must be questions. Jordi again. Oh, no.
Sorry, I was just applauding, so thank you.
Any other questions? So while waiting for another to come up with the questions, what would be the best tracer for the spiral arms then, other than star clusters?
A better tracer of spiral arms.
Yeah.
So the distribution of gas is a very good indicator, but it's harder to tell the distance. Then what is used usually to constrain the spiral arms are masers. So they are very clear, and from radio observations, you can tell very precisely the distance. They have parallaxes from very long baseline interferometry that give very, very good distance estimates, much better than Gaia. But in their studies, they have like 30 masers or something like that. So very good, but few tracers. Clusters are less precise. And first you need an age estimate like we do, and then you need to take just the youngest ones because they are more likely to be associated with the gas. So I think it's a trade-off. The best and most cited, let's say, spiral arm papers and models, I would say, are from those masers distance, because they're more precise, but there's not a lot of them. So I think the multi-wavelength combination should be helpful. It's always helpful if all of your tracers agree. When they start disagreeing, well, maybe you regret having combined tracers and you thought, okay, my life was easier when I was using just one kind of tracers. So what's the best? I don't know, but the approach from different angles, I think eventually it will help us converge to something.
Yeah. Okay. Marcel had a question.
Hi, Tristan. Very nice talk. My question is, what are you up to right now? What are you chasing? What are you doing right now?
I am trying so I would like to do this systematic characterization of the clusters using the new Gaia EDR3 data. So that's my most immediate goal, is just to refine this picture, but with the latest Gaia iteration. But the direction really for the next steps and the next project, that would be to push this idea, and especially this plot. I made it quickly for one cluster, but you can see that for others. Which are the clusters that are gravitationally bound, and which are those that are being completely disrupted? Because that would be one of the keys to understanding this plot. Why do some of them survive for 1 billion years, and why do others survive for just 10 million years? Is it something that happens to them during their life? So, oh, you're lucky, nothing bad happened, or, well, you were unlucky, you just bumped into a giant molecular cloud. So the next open question I would really like to tackle is this. Why do some of them survive for a long time, and why do others die very quickly? There are stars out there, but they disintegrate. But that's not like my next paper. That's more like the next theme I have started working on. Survivability. Yeah. I don't know how immediate your question was. What am I doing this afternoon or next year?
No, what is your next goal?
Yeah, the long-term view is this: explain why clusters survive, and physically, like adding some physics to this. Not all of them are resolved, but nearby clusters are kinematically resolved somehow, up to a few hundred parsecs. I know with Gaia we can do this, we can investigate this region. With maybe the next Gaia, before I retire, maybe we will be able to do this in the inner disk and in the outer disk, and then we will compare. And we say, okay, if you're born in the outer disk, your chances of survival are actually super good. If you're born in the outer disk, well, you have to fight because your life as a cluster will be hard. Might be other questions.
Hey, Maria, do you have a question?
Yeah, it's me. Hi, Tristan. Thank you for the talk. Well, it's very impressive, your results. I have a basic question about the first part. So the idea of using the network, the neural network to derive these parameters. So is this really faster than a typical isochrone fit would be? Because I mean, your training sample is, you have used isochrones to derive the parameters. So most likely the results won't be very different if you would do isochrone fitting, but is this simply that it's faster like this, or what is the true motivation of the use of this network?
So the motivation behind that was, of course, I only showed like two very clean color magnitude diagrams here. But for instance, this one, the isochrones would replicate the shape of the sequence and the hook, but these are called blue straggler stars, and they are stars that for some reason are not turning into giants yet. And old clusters often have that. And if you try to fit a line through this, it will be biased by this. So you need to come up with individual rules. So maybe for this one, I would say ignore stuff that is bluer than something, or you always need ad hoc manual inputs. And here there's a binary sequence. It's a very young cluster, but these are unresolved binary stars. And in other clusters, you might have contamination by field stars that would just be all around. So the machine learning approach makes it possible to treat noisy data, stuff that has binaries in them, that has blue stragglers in them, and very blurred color magnitude diagrams because some regions have patchy extinction. So it's not necessarily going to give the best results. For a very clean thing like that, you could do isochrone fitting. Yeah. And there are Bayesian MCMC sampling, super complex ways. But the machine learning means that you could use the same method for every cluster, the nearby ones, the crappy ones, the noisy ones, everything with the same method.
Okay, I see. Thank you. And I would, or just a comment, I would insist on this idea of Jordi on the velocities, right? Because if you do have some spiral structure, for sure, the velocities must be coherent just by Jean's equation, right? They have to be coherent with the density structures that you have. So, and in fact, now we are exploring, for instance, it's a different topic, but with Oscar and Merced and Xavi, how the spirals in the LMC look like, and we've gathered a bunch of models on how is the signal you expect in VR, in B5, on top of a spiral arm. And yeah, you have a variety of cases depending on the model you have, if you have a stationary wave or whatever. And I'm not sure if anybody has done it recently, looking specifically at this. There are papers looking at the velocities and the systemic velocities with respect to rotation, but I don't know how far they've got and if they have used this recent data. So it's something, yeah, we can look at. Or
yeah, so far, so the best radial velocities are from ground-based spectroscopy, and at the moment, not all clusters have been observed. But the next generation, and I don't mean in 20 years, I mean for like starting this year, next year, of multi-object spectroscopy, they will gather huge amounts of information for that. This will be great for the 3D velocity. So now you have a 6D phase space of the Milky Way. 7D, people who study 3D plus ages, they say they have 7D studies. And well, I think it's a good way to put it. Yeah.
Well, and you should put the chemistry here as well, and then you have even more dimensions. And
exactly, from ground-based spectroscopy again, because the chemistry with Gaia is not that.
No, for sure.
But again, if you can combine Gaia with other stuff, that's going beyond. So far, it's been possible to do everything with just Gaia. That's the thing. In this scheme, I'm only using Gaia observables. And yeah, I wrote at the bottom that I would like, if you have rotation periods, maybe you can constrain the age better. And so combining that with different things. But everything I'm showing here has been done with just Gaia, which I think is remarkable. It's also easier. So that's why we started with that.
Okay, any other questions? If not, let's thank Tristan again. And it's a nice talk, and I think we have a very good discussion. Next week we have Carlos Garcia. I think again the talk will be on Gaia data. And so let's come back in 1 week on the same time. Thank you very much.
Thank you.
Thank you.
Bye-bye.
Bye.